Morning, everyone, and thanks for joining us today. We'd like to start the webinar with a traditional land acknowledgement for the Calgary area where Terence and I are located today. We acknowledge that we live, work, and play on the traditional territories of the Blackfoot Confederacy, the Stoney Nakoda Nations, the Métis Nation, Region 3, and all people who make their homes in the Treaty 7 region of southern Alberta. I'd also like to acknowledge that Guelph, Ontario, where Stewart is joining us from today, is the traditional territory of the Mississaugas of the Credit First Nation of the Anishinaabe peoples. In addition, I'd like to recognize that this Saturday, September 30th, is the National Day for Truth and Reconciliation, which is an opportunity to learn more about the truth and history of Indigenous people in Canada. Once again, thank you for joining us. My name is Gary Winthrop, and I am the market sector lead for oil and gas at Matrix Solutions. For those who don't already know this, our firm is now part of Montrose Environmental Group. I will be moderating today's webinar, which I find to be a fascinating and somewhat troubling situation in Ontario. The title of the webinar is Ontario's Legacy Gas Wells, the Need to Find Them Before We Fix Them, presented by Dr. Stewart Hamilton and Terence Trefiak. It highlights our deep domain of scientific technical knowledge on this critical issue, and now through our access to a broader spectrum of environmental services within Montrose, some advanced technologies that may form part of the solution. The presentation is approximately 40 minutes in length and will be recorded. We'll take some time at the end to address any questions you might have. If you do have a question, you can type it in at any point during the presentation using the Q&A function at the bottom of your Zoom screen, which should pop up as you scroll over that area. Depending on how many questions we get, we'll endeavor to address them all at the end of the presentation, or we'll follow up directly afterwards. We will also share the presentation recording via email afterwards. So now, an introduction to our presenters. Dr. Stewart Hamilton has 35 years of experience as a geochemist, hydrogeologist, and geologist, and has worked in several related disciplines, including electrical geophysics and geomicrobiology. Prior to joining Matrix in 2022, he was the senior science leader for geochemistry at the Ontario Geological Survey, where he worked for almost 28 years. In recent years, much of his research and time has focused on characterizing, mapping, and understanding the regional groundwater quality trends in Ontario's aquifers, in particular those related to legacy gas wells, the subject of today's webinar. Terence Trefiak brings over 22 years of industry experience to the Montrose team, where he currently serves as Senior Vice President of Emission Services. Prior to joining the Montrose team, Terence worked in various engineering positions for companies such as ConocoPhillips and BJ Services. He's an expert in fugitive emissions management and specializes in providing clients with advanced emission reduction technologies for greenhouse gas and leak detection and repair compliance. Terence is a registered professional engineer and is a member of the Association of Professional Engineers and Geoscientists of Alberta. In 2016, he received recognition from Ernst & Young as Entrepreneur of the Year in Canada. Terence holds a Bachelor's of Science degree in Chemical Engineering from the University of Calgary. Stu, I will turn it over to you, and we'll join you again at the end to facilitate questions.
Thanks, Gary. Okay, so I just want to say prior to speaking here that some of this information is from my previous work at the Ontario Geological Survey, but it's all public facing. It's all from publicly available data, and some of the new stuff is actually Matrix ideas and data, and some of that is new, so and very interesting. So I'll just get on here. So I'm first going to talk about the Ontario hydrocarbon industry and try and put it into context. It actually is the oldest, or arguably the oldest industry in the world, in the modern world. People don't realize that. A lot of people don't even realize Ontario has a hydrocarbon industry, but it has, and it's been around for quite a while. I'm also going to talk about the oil, gas, and salt resources database, and this is the record of legacy gas wells in Ontario. There are similar agencies in various provinces and other countries. This is Ontario's, and they have a lot of really important information, and that's important for characterizing the upstream record of legacy gas wells. The Ontario Geological Survey Ambient Groundwater Geochemical Database is a fantastic resource that I'll talk about. It's the downstream legacy, shows that it's a very good indicator of the downstream legacy of gas wells, and that's basically the impact. So when we talk about upstream and downstream, we're referring to the gas problems or gas well problems at source versus the gas well problems that are basically the environmental legacy of these gas wells. So upstream and downstream are terms I'll use quite often. So we're going to talk about the potential impact versus known impact and risk versus hazards, and above all, the need to prioritize. So it is possible to deal with a lot of these issues. I just think that priority is very important. Prioritization is very important. And we're also going to talk, or rather, Terence is going to talk about the new game-changing technology. This is really spectacular. It's a highlight of the presentation, and it's really impressive for someone who's only recently been aware of this technology. It's going to certainly change my life and the work that I'm doing. So I'm really looking forward to using a lot of it. So the key takeaway here is that the managing Ontario's gas well legacy, or petroleum legacy in general, requires both upstream and downstream prioritization. You have to look at where the impacts are, but you have to also look at the source of the impacts. So the first oil well was drilled in Canada in 1858. That's a long time ago for oil and gas. It's actually earlier than the alleged first oil well was drilled in Pennsylvania a year later. But to be fair to Pennsylvania, that well in Pennsylvania was drilled to find oil. It was looking for oil, whereas the one in Ontario was looking for water. And what they found was oil. And to be fair to Ontario too, it did become a production well, produced quite a lot of oil for the time, and had a refining plant there and everything. So it really was like an oil well, and it really was the very first in the modern world. But of course, oil and gas have been extracted for millennia in other places in the world. But gas is much more common in Ontario than oil. In Southern Ontario, um, drilling for gas is very common for landowners, particularly farmers. And the reason is that land granted in most parts of Canada before 1921 had no separation of the surface rights and mineral rights. And so you basically owned it. So nobody really cared except you, what you did on your own land. The government certainly didn't care. And this industry exploded onto the scene very quickly. It was an El Dorado type thing. Everybody was trying to drill their own wells, and gas wells were often drilled by farmers using cable tool rigs. You can see this is an old cable tool rig there from the 1920s or 30s, and but they had them long before that. They could be powered by horses, and they just involve a flywheel and a pulley and a clutch, and you can just basically hammer a tool up and down and up and down. It's basically Roman era technology, and the Chinese were drilling for gas 800 years ago, with complete with bamboo pipelines to in their salt industry. So it's not a new technology. It's been used forever. They would run down these wooden casings between ground surface and the bedrock surface through the clay to stop it from collapsing, and then they'd work inside the casing. And this is actually an old operating gas well in the Niagara Peninsula in 2015 on the left. And that nodding donkey there is not to remove oil; it's to remove water. These are very low pressure gas wells, and water can plug them right up. So they have to remove the brines that seep in periodically. And if that was a big company, that company would have to deal with those brines properly and dispose of them. You can guess as easy as I can what the farmer does with them. I'm sure he doesn't send them off for processing. I suspect they go right into the creek. So the differences between Ontario and Alberta industries are really important because they underscore the problems, and they're the source of the problems that we have in Ontario, and that is that the oil and gas industry started arguably earlier than any other, almost 100 years before the Alberta industry. That was 89 years later. The Leduc field was discovered in Alberta, and that was pretty much the start of the modern industry in Alberta. In Ontario, it started on private land, often by farmers who held the mineral rights. And in Alberta, it's on public land by large operators where the surface rights are held by others. And so that gives a built-in incentive for the farmer in Alberta to keep a close eye on whatever this guy is doing. If he wrecks the environment, he's wrecking the farmer's land. And so he then very quickly reports to the regulatory authorities. And unfortunately, in Ontario, there's a disincentive. The incentives are reversed here. If you screw something up that might screw up your neighbor's well or somebody else's well, you're pretty much going to keep it to yourself rather than run out and tell the authorities so they can charge you. So that is a very important factor in this problem, and it still is to this day. In Ontario, they were exploiting mostly small, shallow gas deposits, which is why the industry took off so fast when it did. In Alberta, they were exploiting large and deeper gas deposits. They'd operated for decades before regulations were developed, and in Alberta, they operated in lockstep with regulations. And finally, the geology is very different. So we have a problem with upward gradients here, as I'll discuss, upward hydraulic gradients. They do have upward hydraulic gradients in various places in Alberta too, but the geology is very well understood, and they've got a lot more depth in which to deal with some of these problems. So and the record keeping on the geology is far better than it was in the early days in Ontario, of course. The reason this industry took off so fast in Ontario was there was already an industry in place, already a market, and that market was for whale oil. Whale oil was in sharp decline, and basically mineral oil just stepped in to fill the decline and took off. And that happened here and happened in the States and everywhere else that oil was developed. That's why the oil and gas industry expanded so quickly relative to other emerging technologies. So in the Oil, Gas, and Salt Resources Library, that they keep the records in Ontario. There are records for 27,000 wells. You have to be a member to get into the inside part of it, but you can get a lot of information just as a visitor on the website. The Alberta Well Database, on the other hand, holds 4 million production records and over 600,000 petroleum wells. Information from 600,000 petroleum wells. That is a far larger data set, and it started far earlier. As in relation to their industry. So challenges in Ontario are poor record keeping and non-existing best practices. People literally didn't know how to drill at the beginning, and they didn't know the problems with leaving an open hole. Or how to abandon a well. They literally shoved in fence posts and just to stop the cow from breaking his leg, and then off they went, pulled the steel out, and that was it. So problematic geology, including the upper hydraulic gradients, as I mentioned, environmental legacy of 165 years of potential leakage and definite leakage in some areas. And that legacy exists today, whereas that never really got off the ground on a very large scale in Alberta because it was being watched. If you're the government and you hold the royalties, you want to know what's going on, or you can't bring in the taxes at the very least. So that's one of the reasons that the system was set up to monitor very early in Alberta. There are no royalties in Ontario because the farmers hold the mineral rights. So M&R is currently in Ontario is currently engaged in a risk assessment of individual wells within this database. And that's a really good idea. It's really important, and we really wish them well on that. That's supposed to take about a year, and that's a huge first step in approaching this problem from the upstream end. So the upstream approach tackling the well problem is to address the well itself. So these are all the wells on the Niagara Peninsula, all these little freckles, and you can see they're mostly in the southern part of the peninsula, and all of the deposits. The gas deposits occur between here and that deep formation there. So this formation is the Queens Formation, and it underlies all these other strata. These are southward dipping, and all the gas. Most of the gas is in the Grimsby or the Whirlpool, which is that little in one of those little tiny strip there that you see because it's actually exposed only at the escarpment. So and then below that is the Queenston Formation, and that's pretty much where the gas stops. So for this, the well records are very important, especially when accompanied by risk assessment for individual wells. And unfortunately, there are likely thousands of wells with no records and thousands more that have poor locations. So this is where the downstream approach comes in, the detection and investigation of the impacts of 165 years of well leakage. So basically, you're using the impacts as a way of vectoring back to where the impacts start. So it's a lot like mineral exploration. We use geochemistry and mineral exploration because the mineral deposits give off geochemical signals, and we follow those back to the source. These are cases where people have caused impacts, and we can follow the chemical tracers back to the source and find them. So there's a big problem with legacy gas wells in Ontario. It's been in the news a lot lately, and rightly so. There was Wheatley, Marintet Beach, Forestry Farm Road. These are all cases where there was major environmental damage or injury or even death. Even some people died. There was another case very recently that didn't make the news. We investigated it last summer. And it was a very unfortunate case where a well owner in Ontario, on the Niagara Peninsula, went into his well to fix something, and he died almost instantly from hydrogen sulfide emissions. So that's not well known. The family wants to keep it mostly private, the location, but they want us to publicize the fact this happened and the circumstances so that this doesn't happen to other people. And this is related to legacy gas wells. So I'll talk a little bit about that. Matrix is currently working on multiple legacy gas well projects across southern Ontario. And despite having being drilled across all of southwestern Ontario, the problems are in three main areas: in the Niagara Peninsula, the Essex Peninsula, and these incised river valleys in the Norfolk Sand Plain in between those two areas. And it's mostly due to geology, the fact that they only occur in those areas. And so that's really important because you need to, with limited resources, you have to prioritize what you do. And this is one of the tools that we would use to do it. It's the Ontario Geological Survey Ambient Groundwater Geochemistry Project. It involved sampling wells, well, basically mostly water wells, but also monitoring wells, so water supply wells. And the black dots here are bedrock wells, the white ones are overburden wells. That took about close to 15 years to do all that. And it's an unusual situation because usually you sample small numbers of samples at a high degree of chemical characterization, or you sample a large number of wells with a low degree. So this is one case where both were done, where they're extremely well characterized, and they're very high density from a regional scale. And full disclosure, I was in charge of that program. So it represents the best record of the current state of groundwater in Ontario, and it's one of the largest databases of its kind in the world. And it wasn't intended to find oil and gas problems, but it did find them, and we were very surprised when we saw them. And one of the reasons was that the major rock and overburden units in Ontario have very characteristic groundwater chemistry. So you can, for any parameter of the 100 parameters, it has a distinctive signal or signature for that particular unit. Like this is a Kettle Point shale, for example. This is the Salina formation up here, and this has quite high sulfate. So we're showing just sulfate here as an example. And so whatever unit you're in, the groundwater reflects the chemical character of that geological unit. And the one exception is the Niagara Peninsula. It doesn't matter what unit you're in, you get the same horrible water quality on the Niagara Peninsula. Very high sulfate, but very high concentrations of many other parameters too. And we didn't need to wait for the analytical results to come back. We saw this in the field, and it was quite shocking how poor the water quality is. And multiple repeat studies have showed similar results and implicated legacy gas wells. So we have done the one main survey. When I was with the survey, we did the one main survey, but we did about 15 graduate theses and a couple undergrads. And this is an undergraduate thesis by Ted Matheson, and he looked at that problem we noticed when we first saw it in 2010. He published this in 2011, and he also got a journal paper out of it, which is unusual for a bachelor thesis because it's a really significant problem. So his thesis was shallow groundwater salinization on the Niagara Peninsula. Caitlin Small did a really good and very comprehensive master's thesis on this a few years later, supported by the OGS and in collaboration with the MNR. And both theses implicated gas wells in the formation of this problem. So I'm going to cut to the chase. We're not going to talk a lot about the results, but there is one. This is what we call the Western anomaly. The Eastern anomaly is over here on the Niagara Peninsula. And this is the central core of the anomaly, and it's defined by the ridiculous sulfur isotopic values we got. They didn't make any sense at all. And the reason is that despite we had concentrations of that were up to gypsum solubility, so extremely high concentrations of sulfate, and yet the delta S34, the sulfur isotopes were far more depleted than the adjacent Silurian evaporite. So normally in the Salina formation here, you'd expect about 30 plus 30 per mil. This core here is -5 per mil at 5,000 milligrams per liter. That is, for a geochemist, that is crazy. We had no idea what was going on. Didn't make any sense, and they're lower than any known marine sulfates in the history of the Earth. So where on earth are these values coming from? Ted found them, and we didn't understand them. And my colleague Kurt Kaiser at Queen's, who was his co-supervisor, couldn't figure it out either. Then Caitlin better documented it. She couldn't figure it out. And in the end, Caitlin referred to them as exogenic, meaning coming from somewhere else. And that's that trend right across there and at the core of the bigger anomaly, which is everything. And so we, this is looking at the groundwater. In this case, this is looking at surface drainage basins from an OGS publication by Abigail Burt. And this is, you can notice here that the exogenic sulfate trend goes right across these surface water drainage basins, which is very unusual. You don't usually have groundwater contamination that crosses basin boundaries. and it even crosses the groundwater basin boundary. So they're slightly different. The drainage divides from, this is from Ted's work, and the groundwater flow direction is orthogonal to the direction of these, meaning that tells us one thing for sure, that this impact is modern, and we say likely anthropogenic. It pretty much has to be anthropogenic. This is a fairly recent, in the last 100 years, this has happened. It hasn't moved down the flow system yet. It hasn't been dispersed out. This is not due to a natural process. This is something weird, something coming from below. And we actually know now what it is, and I'll get to that in a second. So the source looks like terrestrial evaporites. So terrestrial evaporites are like white sands, New Mexico. You have these gypsums that form inside continents, and that didn't make any sense to us. We didn't even think about it at the time, but it turns out we did a follow-up study, and the Queenston Formation, which we thought was a marine shale, is actually a terrestrial shale. It actually forms on the margin of continents, like this is in the Bay of Bengal, and you can see that these huge mud flats that form, all of the sediment and all of the dissolved solids here come from the Himalayas. And if this environment were very, very dry, like it was in the Ordovician in Ontario, then we would form gypsum deposits like we see all through the Queenston Formation. So it turns out that those exogenic sulfate values are coming from the deep Queenston Formation, which underlies everything. And so the question, of course, is how does that happen? Well, it happens, we think, because this is the Allegheny Plateau on the American side. This is Lake Erie. The scale here is enormous. It's 400 kilometers from one end to the other. And this is flat as a pancake. Toledo, Ohio is down here. Cleveland's right here. Niagara Falls is up here. And extremely flat on the Canadian side. We have some relief up here, but it's nothing like the American side. And the strata dips upward towards the north shore of Lake Erie. And interestingly, on Pelee Island, when we were surveying out there, we were stunned to see that the entire island, the bedrock artesian levels are up to 4 meters above the lake level. And the whole island is very flat. It's basically a little bedrock knob that sticks up, and it's flat as a pancake. And yet the hydrostatic heads in the bedrock in water wells on that island are 4 meters above lake level. The only place that pressure can be coming from is the American side. So this is on the scale of the Great Artesian Basin. You're pumping up your pressures here in Allegheny Plateau, and then it's getting trapped under Lake Erie, because Lake Erie is an incredible aquitard. It's clay bottomed with glacial lacustrine clays and then lacustrine clays on top of that. And there's nowhere for it to get out except this little window on Pelee Island, and here and there along the North Shore, and then of course on the Niagara Peninsula. So here's the Niagara Peninsula. It's actually an isthmus, not a peninsula, with the Niagara River running through. It's far higher relief on the U.S. side, of course, and underneath is the Queenston Formation, which is an aquitard. So it's trapped. These pressures are trapped between this aquitard here, and they can pop out somewhere on the peninsula. And there's a cross section across the peninsula from the American side. So we have the Allegheny Plateau up here, 400 to 600 meters elevation, 174 Lake Erie, 74 in Lake Ontario. And then so the deep hydrostatic heads would be very high. If we resolve this into hydrostatic hydrostratigraphy, we would get the yellow aquifers, and we've got the gray and the red aquitards. And in the upper part of the salina formation, it becomes an aquifer from an aquitard as all of the gypsum has been weathered out and breccias formed. So you get fluids moving, a recharge up here. Everywhere where the red line is above the blue line, you would have upper hydraulic heads. So you would get natural flow at the Portage Escarpment on the American side, the Onondaga Escarpment on the Canadian side, and of course the Niagara Escarpment. And we have things like the Upper Canada Salt Mine and Sulphur Springs, or it was called the town. And these are all because there's natural flow. There's natural flow by this system. But then you come along and you punch thousands of little gas wells through there, and then walk away when you don't find anything, or even walk away when you do. And that connects all these strata, and it short circuits the system, and it allows deep fluids to move up and pollute the shallow aquifer. So particularly these shallow karstic limestone aquifers that we see. And we think that that's where these plumes are coming from. So the question is, why did it happen right there? Well, one clue is that we have high ground to the northwest. We got low ground to the northeast, to the southeast, I should say. But in this low ground, it's capped by very thick drift. So in this case, thick drift, it means darker colors. darker colors are thin drift, lighter colors are thick drift. So this is all thick drift. If you want to find a line across this peninsula where the drift is thinnest at each one of the formations, in each one of the areas. So this is called the Salina Trough. There's a place where the drift thins in there, and it's the thinnest you'll see, about 20 meters. And here it's basically almost rock outcrop, and it is rock outcrop here. So where the drift is thinnest is a window between the two pressurized areas, this part of the peninsula here and this part here, and I guess that's why the exogenic sulfate comes up there all the way up from the Ordovician, bringing that sulfate with it. And so this is a point of deep pressure relief, I assume. It doesn't just occur there; it occurs in several other places in southern Ontario, particularly down on Essex Peninsula, and it's defined as having very high sulfate along with that weird sulfur isotopic composition. So there's a million more things we could talk about these areas, but just in general, we know an awful lot about them. We still need to know more, but we know that how this ends up causing a lot of the problems. And one of them is that low concentration, naturally occurring hydrogen sulfide is widespread in Ontario. Half of all wells have it. At high concentrations, it's often related to human drilling activities and infrastructure, and either directly releases H2S as sulfur, water, or sour gas from the deep formations, or more commonly, it brings together the two incompatible materials. And those materials are methane and sulfate. And you'll notice that the methane, this is a distribution from the Ontario Geological Survey. The methane there, lots of we have a problem here. When I say natural, I don't mean natural gas. It is natural gas, but I mean it's not anthropogenic. So we have lots of natural methane in there, natural methane here, and then we have this sulfate here. Notice that we never see sulfate and methane in the same place. So even in the shales, we see in the Collingwood shales we see methane, but we don't see sulfate. And in and in the red shales here, the Queenston Formation, we see methane, but we don't see any sulfate, but no methane. So the two don't go together, but when you put them together, the byproduct is hydrogen sulfide, and that's because bacteria basically form it. So if you look at all the data together, you see either methane on one side, sulfate on the other, but you hardly see any that have both. And where you do see both, the hydrogen sulfide concentrations are very high. Most of those are actually off the axis. You don't see it. And the highest H2S samples approach the origin because one or both of the reactions are being completely consumed. And only 3 of the 41 with H2S greater than 10 milligrams per liter of no methane. It turns out almost all of those are due to gas wells. And so in groundwater, when they get together, they form bacteria, go crazy. They love it. I'm just showing you the wrong bacteria. This is sulfur oxidizing bacteria, but you can't really take a picture of sulfur reducing bacteria. It's just black slime. So what happens is that you either bring the methane to the sulfate or bring the sulfate to the methane, and they don't naturally coexist. You can either bring up the methane by buoyancy and then meet into the sulphate-rich aquifer, or bring the sulfate fluids up by these upper hydrostatic pressures into a methane-rich aquifer, and either one will produce hydrogen sulfide. So here's where we have it. All that blue right there, those are the natural sulfates. Notice that there's hardly any thermogenic gas in there, thermogenic meaning from deep sources. The black ones here are thermogenic gas, or there are cases where we think there's thermogenic gas based on sulfate reduction that we're seeing, unexplained sulfate reduction. So here we get into the why this is such a serious problem. So hydrogen sulfide in groundwater, there's about a 10 times increase in air if you've got the two equilibrating by Henry's law. So if you've got 1 milligram per liter in air, you could get up to 100 milligrams per liter in groundwater. By Henry's law, the concentration are related, and so about more than a quarter of all groundwaters are above the short-term exposure limit in air, or can produce air that is. A great deal are above the 100 ppm limit, which is a lower lethal limit, and 1% of groundwaters in specific circumstances can produce hydrogen sulfide above 1,000 ppm V, and that's the instant death limit. In that case, where they have the fatality, we measured 12,000 ppm in that well that the poor fellow climbed into, and that's where the concentration was, right up there. So aeration to remove H2S can be extremely dangerous, but in the course of my work, I've found tons of cases where people are doing it. This is a very dangerous case in a barn where somebody was doing it, and this idiot here is sampling, leaning over and sampling it. That idiot was me. And this is aeration. This is a little safer. It's outdoors. This is extremely unsafe. There have been literally thousands of people that have died from H2S over the years in cases like this, climbing down into low areas. H2S is heavier than air, and it just pools down there. And this guy's spraying in there to get rid of the H2S. So it's just crazy. And this is a safer system outdoors, much safer. So the domains, here we are. This is in Ontario. These are the very high concentrations. Most of these are OGS data that we just downloaded, but some of these are matrix data and public-facing matrix data. So dissolved hydrogen sulfide measurements by OGS and matrix, and a few of ours. And you'll see here that this is natural gas in the central area, and we're not seeing much in the way of H2S production here, because that's where the natural gas is. When gas comes into this area, thermogenic gas, you wouldn't really notice it. It's just blue on black. It's just a match on the fire kind of thing. It doesn't make any difference. These few cases where we see it are natural cases or cases related to water wells, and I won't really go into them. Down in the Leamington area, we see deep fluids and deep gas. In the Norfolk Sandplain area, these are incised valleys that cut down so deep that they reach that potentiometric surface, probably influenced by the Allegheny Plateau. Same down here. And then up here on the Niagara Peninsula. So those are very high hydrogen sulfide concentrations, far above everything we see here. Above this size is enough to be lethal, and there have been several cases where it's happened now. So when we see H2S in the shallow aquifer, it does not originate from the same formations as the gas or the exogenic sulfate. So I'm just going to kind of summarize here before we move on to Terence. Most problems are caused by multiple unknown point sources of gas and deep fluids leaking into the shallow aquifers. In some areas, deep sulphate-rich fluids rise from one stratum and methane rises from another, and then they enter an aquifer where neither existed before. We see methane and sulfate meet by any means, and when we see that happen, hydrogen sulfide is generated almost always. And in wide areas where methane is naturally occurring in the aquifer, we see almost no H2S documented. So that's not something we completely understand. We have some speculation as to why that happens, but that's really important because it narrows down the areas we need to worry about when we're prioritizing. So the most serious things occur when methane gas actively leaks into aquifers where it does not naturally occur. And that leads to gasification of the aquifers, which causes leaks and maybe into people's basements. Or if there's sulfate there, it'll create toxic hydrogen sulfide gas. So this is why this new technology that Terence is about to talk about is so exciting. I'm going to pass you on to him.
Okay, thanks, Stu. Yeah, so as Stu mentioned, there's new technologies. In the last 10 years, a lot of the technologies have been developed to find and measure methane emissions, whether it's from inside a facility or across a wide area. So this is a methane detection triangle where I'm kind of, have the different technologies layered up and show the differences. We separate the technologies into what we consider micro technology and macro technology. So micro technology would be something like an optical gas imaging camera or a handheld detector where you're taking it to find an actual point source and say that valve or that well is leaking. Whereas you have a macro technology to determine over a wider area where the emissions are and how big they are. And as you move up into these different technologies, your survey coverage will increase, so your area that you can cover in terms of time is larger, but your resolution is decreased. So, for example, satellite detection, you can, cover very wide areas of land, but your lower detection limit is quite high. So you're going to see if you had, a very high well capacity with just flowing to the air, a big blowout, you're going to see that with a satellite. But you're not going to see a very small emission or even a medium or we can consider a large emission on the surface area. When you move down to fixed wing, which is basically manned airplane with either a LiDAR or other technology determining if there's methane, you get a larger coverage, not as large as satellite, but you get a large coverage, and your resolution is better than satellite, where you can get down to kind of large, very large to large emissions. But again, it usually has to be a point source. So if you're looking at gas coming out of a underground well and it's diffused over a large area, You may not see that with a fixed wing detection, but you would catch any larger emissions. Maybe you have wells that have higher venting or higher leaking, and you might catch those very large emission sources. Then you move down to mobile, which is vehicle-based, and then drone, which is unmanned aerials, and sensors, which is a sensor array, and then right down to the micro. And then I'll talk more about the mobile aerial and OGI, which is some of the services that Montrose provides. Next slide. So some of the micro technologies, one of the main ones we use for most of our surveys is optical gas imaging. So it's an infrared camera that can see hydrocarbon gases. And you use this, an operator would use this and look through the camera and walk through a facility or walk around and see emissions. You can also attach these to drones as well to cover large areas. And then you have point source technologies where you're walking a pipeline or just looking for emissions across the ground. Next slide. This just shows some video footage of some emissions coming right out of the ground. So you can see in the picture on the left, you can actually see the shadow of the technician there, and he's filming some emissions that they found coming out of the ground. Basically invisible to the eye, but they'll be visible with the camera. Next slide. It's another one at a facility where there's a fairly decent sized underground leak coming over a large area. Again, you'll be able to see with the camera quite easily. Again, you can cover a very large area with a camera, but it's you're limited to how far you can walk or you can put this on a drone. Next slide. So for mobile methane emission monitoring, which for the problem that Stu's talking about here, where you have a very large area, and you're not sure exactly where the potential well sites are, and you need to cover a large area, this would probably be one of the better technologies, where you can drive with a very, very sensitive methane detector. You're collecting wind direction and magnitude, and you can actually triangulate as you're driving and determine where there's emission sources coming from. And again, cover a large area. And really what you want to do is reduce this area that we're looking at for this problem is very, very large. Hundreds of square kilometers, or even thousands of square kilometers. You want to reduce that down to maybe dozens of square kilometers so that you can use other technologies to then find where the problems are. So this continuous monitoring with a vehicle-based could cover a large area and is very, very sensitive. So you can pick up very, very small emission point sources, and then you can actually use that to triangulate down to where the sources are probably coming from. Next slide. And this shows an example of this is a vehicle driving fairly fast and driving past landfills, and showing how you get those spikes from fairly low emission, wide emission sources across a wide area, and you can pick that up. And then even going over a small lake where there is natural decomposition can pick up that natural methane from decomposition. Next slide. This is some of the mobile mapping. So this is visually how you represent it when you're driving, and you can pick up, this is actually parts per million in one of our vehicles, but you can do the same thing for methane or other air components. But basically, as you drive, you can pick up and chart it, and then actually triangulate. And on the next slide here, I'll show some of what the triangulation will look like. So once you find an area where you have elevated emissions, you can then stop the vehicle and collect data, and then triangulate and actually map out or create a concentration map of where those sources are, and figure out where the highest concentrations are, and then have the information to go after those potential sources. Next slide. Drone surveys are also applicable type of technology for this type of problem. This particular drone uses a laser-based system, so it shoots a laser down that can determine the parts per million meter of methane concentration from from where the drone is at altitude down to the surface. And you can basically send these drones out autonomous, and they can cover a fairly large area of land. and then can report back with a map, again, a concentration map of where the sources are. So in this particular problem, you may combine vehicle-based detection, or even aerial-based to find the really big stuff, vehicle-based to find the areas of higher emission sources, and then drone-based to really pinpoint on where the specific sources are. And with drones, you can combine optical gas imaging as well onto a drone, so you can visually see, potentially see the emissions. You can put on magnometers, magnometer to again, used quite commonly to find abandoned gas wells, to the metal of the well pipe. And then you can also put in visual cameras just to see visually what you're looking at. Next slide. Yeah, you can just pop through these 4 pictures here. So this is a facility that we did with a drone. Again, we know this facility has emission sources, so we have a fairly tight survey path for the drone. But once it does do this, it took about 15 minutes to do this one facility. We then have the information to lay out the concentration map and then focus our optical gas imaging survey to actually find out what these sources are and how to fix them on this site. In a well site application or abandoned well site application, I mean, you can cover a larger area, have probably a looser flight pattern to cover a larger area, and then again, pinpoint out and get the concentration areas of where there potentially could be methane. Next slide. This is another example of a landfill. So again, this was a drone survey done with across a landfill, and it shows the hotspots on that landfill of where there's potential emissions. And again, with a problem like this, where you have wells, very, very old wells that could have migrated gas, coming out from underground over a large area, or they could be a point source coming, out of a small area underground. But combining these technologies is really the key. So right from, potentially fixed wing, mobile methane, drone, and then right down to even having, a technician walk around with a camera to actually find out where the sources are. So I think the answer, I mean, there's a lot of really fascinating technologies out there that could help to solve this very serious problem. I'll pass it back over to Stu.
Thanks, Terence. Okay, we'll just sort of a summary here. So upstream prioritization of petroleum wells, MNRF is currently conducting a formal legacy well risk assessment. We really wish them well on that. That's an extremely important component of understanding what wells are most likely at risk and where the sources might be coming from. The results of the assessment are key to addressing legacy well problems, and mainly in the upstream side of things. This will help focus scrutiny on a smaller subset of wells that could be at risk of leaking. And this could be followed up by rapid screening, just like of the type that Terence was talking about, of individual wells or fields by modern remote sensing technology. You don't even need to have access to the land. You can get certain permits and whatnot, and you can look at it from a distance and perfectly easily. So downstream detection is a different approach altogether. It may be faster and more cost effective. It would be using the 165 years of environmental impact really as a way of, to our advantage, as a way of revealing the most serious areas of contamination first. So you focus on those. That isn't just because that's where the main leakage is happening. That's where the main damage is happening. And you really want to get the best bang for your buck, especially at the beginning of this program, this type of a program. So publicly available groundwater geochemical databases already identify regional contamination in areas where the natural methane emissions are low. But more importantly, it also shows huge areas where there is no impact. And even although an awful lot of drilling was in that central area where all the natural methane existed, there was no problem with either methane or with upwelling of deep fluids. We don't even really understand why that is. We have some ideas, but that's something maybe for another talk. But such areas would be ideal for methane sensing technology. These areas where there aren't high natural methane, and suddenly it's being put into the aquifer. It's not sensing hydrogen sulfide, but wherever you get methane and sulfate together, you're going to be having hydrogen sulfide. So it's a proxy way of detecting where the really dangerous areas are. So just to summarize the whole presentation here, Ontario has arguably the oldest oil and gas industry in the world. Unfortunately, the early construction methods and record keeping were very poor, and they remain poor to this day, and not to no fault of the people that are keeping the records. And 27,000 recorded petroleum wells, but the problem wells are probably only a few thousand. So the M&R risk assessment hopefully will help to narrow down some of the types of wells that will be problematic, but the serious legacy environmental problems occur mostly in 3 regions. Upstream and downstream prioritization should happen together, and this is before major abandonment investments. If you go and you can spend millions on a single well, and if it turns out that well is not a huge problem, you shouldn't be putting money into it. And this requires the use of existing public data combined with modern remote sensing technology. So I really think that we can fix this problem. 10 years ago, I would have said otherwise, but having studied it for 10 years, I would say this really is resolvable, and it just requires that we do it right and in the right order. So if you want to contact us, there's our contact information, and we're happy to talk about this with anybody. And if you have any questions, we're happy to take those too.
Great, thanks, Stu and Terence. We do have a few questions in the queue. The first one for you, Stu, is did you measure other major gases such as carbon dioxide, nitrogen, and oxygen? And if so, did you see any correlation with methane or H2S?
We did some follow-up studies. We published a couple journal papers on this where we did measure nitrogen and, well, a whole raft of gases. And we, as a non-routine portion of the ambient groundwater study, when I was with the OGS, we were measuring many other gases, and like I said, published a fair amount on it. But as part of routine measurement, the measurements that were taken, the gases were measured were carbon dioxide and methane, and that's it.
Okay, the second question for you, is there any relationship between Ontario's breathing well region and methane H2S distribution?
No, not at all. And the breathing well is an extremely interesting area. By the way, the breathing well area was first characterized as part of that ambient groundwater study. We were taking unscrewing some well caps, and suddenly the caps blew off. And then anyway, it's a fascinating area. It's the world's largest breathing well field, as far as we know. And my colleague and former student, Candace Bocking, I should say now, and she did a master's on that. So very interesting. We know a lot about the breathing well field, but it's an oxic environment. Oxygen gets sucked down during these huge breathing events by thousands of wells, and then during a high pressure system, the air gets pushed down into the cavern systems, and then during a low pressure system, gets blown back out again. But it's minus most of the oxygen. But not all the oxygen is gone. There's still about up to 4 or 5% left. Very serious asphyxiation hazard. You can empty an entire house out of oxygen in a matter of minutes, but it's still an oxic environment, technically speaking, and therefore there's no methane and there's no reduced gases of any kind, H2S or methane.
Here's another question. How do you differentiate natural hydrocarbon seepage from those related to legacy wells? Morris in 1994 highlighted natural anomalies, surface seeps in Essex County in areas where there are no legacy wells.
Yep, it's mainly with isotopes. So we look at the isotopic composition of the methane, or in some cases when there are more hydrocarbons, we'll use higher hydrocarbons, but it's generally methane, and thermogenic gas is quite distinct from biogenic gas. And we also know the isotopic composition of a lot of the formations. There was some great work done by Mitchell Scoose and some by supported by the Ministry of Natural Resources, where they identified the isotopic composition of the various gas pools. And so even in cases where there's some confusion about the isotopic composition of the carbonate of the methane, you can look at the local gas pools and see what they were, and basically fingerprint the methane using isotopes. So yes, there are natural seeps. They're generally biogenic natural seeps. On a very rare occasion with a deep fault, you can have a thermogenic natural seep. But my guess is that even those, I think if you look very carefully, we'd probably find those are related to gas wells. Because if you think about it, that gas has been there for 300 million years. And if it was leaking out with every fracture, it would be long gone by now. So in order for it to remain there, there has to be a good tight seal. and that's why it's so rare that it comes out naturally.
Okay, I have a question now for Terence. If there is a land developer looking to build on a specific parcel of land in one of these high-risk areas, could you use some of the airborne technologies to risk screen a specific site before they break ground?
Yeah, for sure. In an application like that, probably something like the drone survey to map out where, if there is any concentration of methane in the area, even combine it, if it's a, few acres of land, you could even combine that with a walking survey with potentially sensors, or even just a walking survey with an OGI camera or a other kind of handheld detector.
Okay, great, good question. Another one for you, Stu. Have you looked at existing hydrocarbon micro seepage surveys, such as Gallagher R&D 1984, in the Wheatley area to identify potential legacy well locations?
I haven't done that. I've done a lot of work on Wheatley in various capacities, but I haven't done. We haven't done much sort of background. You could consider that background work, where you're looking at background seeps, and I know they occur. Again, we're going to have to be at some. There'd have to be a fairly detailed study to determine how many of these are really natural. Don't forget, when I first saw a lot of this stuff, I thought, holy Moses, I didn't know. It was so widespread, we thought it had to be natural, but it became very apparent eventually that it's not natural. It's just because we had 165 years to spread this stuff around, and hardly anything we've seen, any of these poor water quality issues are natural. There are huge problems in the Ottawa area from salt, from Champlain Sea, but that's a different issue. Most of these huge problems are actually related to legacy gas wells.
Okay, sounds good. We don't have any other questions in the queue at the moment, so if you do want to fire one away, get it in there quickly, and we'll try to address it. And again, if you come up with other questions afterwards, don't hesitate to reach out to Stu or Terence or myself, and we'll get back to you as soon as we can. Okay, there's another question in here now. Understanding this will take another year to define these areas, what are the next steps?
Well, right now, I can only speak to what M&R is doing right now. I think you may have heard that the provincial government put aside about, I think it was $23 million for this. That's a lot of money for characterization. For remediation, it's a very small amount of money. It's going to cost a lot more than that, which is why characterization and prioritization is so important. No matter how much money you spend, you want to spend it. You get the best bang for your buck, and you want to get your results early, and that's why you need to prioritize. So the M&R risk assessment, again, we're not involved with it. I really wish them well and hope it's done well, but it's really important to do it well. And it's important to include all the factors such as geology. But of course, it's going to presumably be a work in progress, so they'll have to update it. But once that's done, I don't think that they should be using that exclusively. I think they should be using some downstream indicators as to where these problems occur. And some of them you don't even need. You need geochemical data. You just need to find out where people are complaining the most. In the Forestry Farm Road area down near Norfolk, you just have to drive down the highway and you know where the problems are. You can smell them. So these areas that they know of are right now pretty high priority, but there are some areas that were under covered. The Six Nations was undercovered by the Ontario Geological Survey work, and that was partly my fault. It was by mistake. And so there are areas that should be beefed up, and the downstream end, the impact end the information should be improved somewhat. But there's enough to start working with right now, and I would recommend that they start doing a very similar thing, that they start doing a risk assessment on the other side, on the downstream end, and say, where are the worst problems? And then put those two data sets over top of each other like a Venn diagram, and then start working in the areas that are highest priority. So that's what I would recommend. We have our hands full right now doing all kinds of projects in Southern Ontario, but there is need for more work. So I hope M&R can prioritize this adequately.
There's another really good question here. As we start remediating these wells, will the others become worse as the gas finds the next path of least resistance?
that is a definite possibility. That can happen, and we think it has happened in some areas. So it has to be done carefully, and you always have to be doing it with science. You have to keep your eyes open. You have to have good control information, so background information. You have to do surveys ahead of time to make sure you know what the current situation is, and then monitor. And so you need to monitor not just groundwater quality, but you should be monitoring pressures. So these are not expensive things to do. You just simply put a few pressure loggers down people's wells, and you monitor them and make sure there aren't changes. And if there are, then you have to address them. So it's a matter of in some cases you're definitely going to have to make choices, but this problem is not going to get better. It's going to get worse. We're only getting into as I said, it takes hundreds of years for some of these flow systems to reach this groundwater to reach the end of the flow system. So some of this stuff is going to get worse for a long time before it starts to get better naturally. It might even be the next glaciation before it gets better naturally. So we don't want to wait till then. We want to do what we can now, but certainly there's things that can be done without impact, and if there is impact, then deal with it. We'll have to deal with it.
Great. That's all we have for questions. So I think we will wrap up. And again, if you have any more burning questions later, don't hesitate to reach out. We will follow up with an email and a link to the recording of this presentation. And thank you everyone for joining us today. Really appreciate it.